So OpenMM is based around a layered architecture, and it's got a lot of layers, and here's an architectural diagram of it, which you mostly don't need to worry too much about how this is all architected. The important things to notice is that we've got at the top the sort of high-level Python application layer that you saw in the earlier talks. And then sitting below that is what we call the OpenMM public API. And then below that, those are sitting on a whole stack of other layers down to, at the very bottom, we have like low-level computational kernels running on your GPU or whatever. And we're not going to be talking really about those layers at all in this workshop. We're going to be focusing on the higher-level layers. So we've seen the top-level one, and in this talk, I'm going to move down one step and talk about the OpenMM public API. So why would you want to use this? It really depends who you are and what purposes you want to use OpenMM for. So I told you before that one of the ways that you can use OpenMM is just as a library. You're writing applications, you want to perform molecular simulation type calculations in your program. And so the public API is how you use OpenMM to do that. Now, for those of you who are more chemists or biologists and who just want to run simulations, you don't need to use the OpenMM public API, but it is there if you want it. You can use it in your control scripts. You have complete access to this. And as you will see, there's really an amazing amount that you can do with it. So although you don't have to use it, you may really quickly decide that you want to and that there's some great stuff you can do by using it. So let's talk a little bit about how the API is designed. The first and one of the most important goals of it is we wanted it to be really simple. It should be easy to learn and easy to use because we wanted lots of people to use it. And one of the things that I think all programmers learn very quickly is that if something isn't easy to learn and isn't easy to use, then most people won't use it. There's actually an interesting corollary to this when I say easy to use. That includes not just easy to use, but easy to use correctly. We try as much as possible to design it in a way so it will always guide you in the way of doing the right thing, because there's, molecular simulation is a really complicated field, and while we can't, build in all sorts of magical intelligence, we do want to make it so it will sort of steer you in the direction of doing intelligent things, and that if you do the obvious thing, that will be the right thing. Another really important goal of it is that it should be extensible. We are a very small team here. There's essentially an infinite set of things that people might want in a molecular simulation package. No way we can implement all of them and provide them to you. So we wanted it to be extensible so that other people can define new force fields, can define new integration methods, new algorithms, etc. And in fact, OpenMM is built entirely around a plugin architecture so that people can write new pieces of code that interface with it and add new features to OpenMM. Another side to extensibility is not in terms of the features it provides, but in terms of the hardware that it runs on. Hardware is changing really, really rapidly. New types of processors are coming out continuously. It's really difficult to predict what we'll need to support just a few years from now. And so we wanted to make it modular in the sense that it's easy to create new implementations of all the features of the library to support new types of hardware and then to just plug those in. Another interesting aspect to this is that we wanted it to be possible to implement this API efficiently on a wide range of hardware platforms, which actually turns out to be a very subtle thing because it's very, very easy to create an interface that has assumptions built into it that don't match the assumptions of, or don't match particular types of hardware. When you assume that particular operations are fast, particular operations have low latency, various things like this, it would be really, really easy to design an interface that was very efficient on the first platform you implemented it on, but then when you tried to implement it on something very different like, a supercomputing cluster, you'd find that you'd made assumptions and this interface just could not be implemented efficiently, and we've tried to avoid those problems. And finally, we wanted to make it very easy to incorporate it into existing code bases, and we will, in fact, be talking about that later this afternoon. Choice of language. So the core of OpenMM is written in C++. It is natively a C++ API. However, we also provide wrappers for it for Python, C, and Fortran, which for the most part expose all features of it. So almost everything that you can do with OpenMM, you can actually do in any of those languages. The only exception is that if you want to write plugins that add new features, those have to be written in C++. All right. Now I am going to take you through the API, and I am going to cover the entire thing in 3 slides. So it's not very complicated, but I'm going to introduce you to all the important classes and the concepts involved in it. So the first very important class, which in fact you have already seen in some of your scripts, is called system. So we sort of define a system as being, I like to think of it as the mathematical system that you're simulating. Other people might think of it differently as, you know, a chemical system or whatever, but I think of it much more as a mathematical system. But really what it defines is a collection of particles. It says this is the set of particles that we're working with. It specifies what the mass of each particle is. It can specify a list of distance constraints that are, you know, the distance between these 2 particles must remain fixed. And it also defines what are the interactions between these particles, but it doesn't do that directly. It does it by just providing a list of force objects, and I'll get to force, I think, on the next slide. So system is really sort of the static, unchanging properties of the thing that you're simulating. It's the things like, you know, what are the set of particles, what are the set of interactions. Everything that actually changes over the course of a simulation goes into a different class called context. So the context is basically all the variable information about the current state of a simulation that you are running right now. It is things like what are the positions of all your particles, what are all of their velocities, and it can also have other sorts of parameters, but things that can change continuously over a simulation. Force is what we call an abstract class. So there are many subclasses of it that each describe a particular type of force. And really, a force just means anything that affects the behavior of the system. It's actually a slightly misnamed class. It does, in fact, define forces. A force object can apply forces to particles. It can apply, contribute to the potential energy. But it also can do a few other things. For example, it can define adjustable parameters that vary over the course of your simulation, that get stored in your context, and that affect what happens. And it also gets to modify the state of to modify the context, like your positions and velocities and your parameters at the start of every time step. So it can actually be used to implement things that are a bit more than just forces. For example, some thermostats and barostats are actually implemented with force objects. I would have come up with a better name for it, but I tried really, really hard, and we never got a better idea than force, so it's still called force. And most force classes are, in fact, forces, but there are a few others.
Are they really potentials?
No, because again, it could be like a thermostat or a barostat, which are not forces in the standard sense. They don't contribute to the potential energy, but they do affect the behavior of the system.
So it sounds like you could define a constraint as a force as well.
Potentially, it could be, although it would be very hard to do it efficiently.
So let's say you wanted to integrate a rigid body constraint on your peptide. You don't want it to rotate, for example. How would you implement this?
Actually, that's a really good, something that we're talking about doing right now, and there are actually a few ways that we're considering about doing it. One option is to do it with virtual sites, which are, a virtual site is like, it's a particle, but instead of its trajectory being integrated according to the equations of motion, it's simply its position is recalculated at the start of every time step. And so one way of doing it would be with that. The other way of doing it would be to have an integrator that specifically knows about rigid bodies and knows how to integrate the equations of motion in a way that preserves those constraints. Oh, and another way is to just implement it with distance constraints, which we have built in. Integrator, I just mentioned, is something that advances the system through time. It defines an integration algorithm, and you've already heard about the list of integrators that we have. So, a fairly large number of different methods that you can use for advancing the system through time. One other class, in fact, our final one, because this is slide 3 of 3, is called state. A state is like a snapshot of the simulation. So it is created from the context, but it is immutable. It's used just for reporting. So you go to the context and say, all right, I want information. Give me a state that contains a snapshot of what is in the context right at this moment. By the way, this is the only way to access any sort of state information like positions or velocities. It can also include forces, energies, and various other things. And this ties back to what I was saying before about wanting an API that can be implemented efficiently. If you were used to writing MD codes that, say, just ran on a single ordinary CPU, you might think, okay, well, we've got our position stored in an array in memory, and we can have a function that says, oh, give me the position of particle 15, and this is great, and all is good. And then you run it on a GPU where all your positions are stored in the device memory, and if you want to query any positions, you have to transfer that over your PCIe bus, which has a latency of about 10 microseconds, or even worse, maybe you're running on a cluster, and the position of that particle isn't even on this computer, it's on some other node in your network, and you've got to transfer it over the network. And so we tried to make it so that you can do this efficiently. So when you create a state, you know, first of all, that this could be an expensive operation. And also, you specify in advance all the information that you're going to want. Do you want positions? Do you want velocities? Do you want forces? And this allows us to go and get all of the information and transfer it over in an efficient way. And so creating a state is the only way of getting back state information about your simulation. Okay, so now I'm actually going to walk through some examples of how you actually do this. Do we have like a pointer or anything like that? Don't worry about it. It's not important. I can always just use the mouse here. Basically, the first thing we're going to do is create a system. Now, in the scripts that you saw before, the way you did this was you had like a force field object, and you called create system, and it returned to you a nicely created system object. Well, what I'm going to show you here is what that force field object is actually doing. When you tell it to create the system, it is essentially going to do exactly the same things that I have shown on these slides. Oh, thank you. So you don't have to, the force field can do it for you, but you can also do this directly, or you could take the system that was given to you by force field and then modify it as well. So we're going to create a new system object, and then we're going to tell it what particles are in the system. So I'm going to assume that we've already got somewhere a list of particles we want to add. So for each one, we're going to call add particle on the system, system.addParticle, and we pass to it one piece of information, which is the mass of the particle. There we go. 3 lines in, and we've already got a system object, and we've added all of our particles to it. Maybe you want some distance constraints. I'm going to assume here that we've already got in memory here a list of what constraints we want. So we're going to loop over them, and for each one, we'll call add constraint on the system. And for each one, we tell it the indices of the 2 atoms that you want to constrain the distance between, and what distance should it be constrained to. So there we are. That has just created our system. It has added all our particles. It has set up all our distance constraints. Any questions about that?
Where does this mass come from?
Wherever you want. So I'm assuming here that, particle is like some object that you have defined somewhere. I'm just assuming that you know what particles you want and what the mass of each one should be. OpenMM doesn't care where that's coming from. So, for example, in that case, when you're using the OpenMM application layer, so remember, that's a higher level of the architecture that is actually built on top of what I'm describing here. So in that case, it has a topology. Topology is a class defined at the application layer, so it's a higher level class. The topology object defines a list of atoms. For each atom, it says what is the element of this atom, and from the element, we can find out what the mass is. I think it may actually, in addition, store a mass separately to like distinguish between hydrogen and deuterium and things like that. But this is assuming like you are writing your own program. You want to add molecular simulation features to that program, and from somewhere or other, you know what atoms you want to simulate. Does that make sense? Okay. So you've set up your particles. Now you want to apply some forces to those particles, and OpenMM provides a whole bunch of different subclasses of force, so particular types of force that you can add. So here's an example. By the way, can everyone read this? Is the text large enough? Okay, great. So we're going to create a harmonic bond force object. It probably will not surprise you to learn that harmonic bond force implements harmonic forces between particles to implement bonds. So I'm going to assume, again, here you've somewhere got a list of what bonds to add. You know what bonds you want. And for each one, we're just going to call add bond on our bond force here. And we pass in the indices of the two atoms that you want the bond to connect. What should the equilibrium length be, and what should the spring constant be? And finally, after you've done that, you've set up this bond force, or this harmonic bond force. Now you need to add it into your system. And you just call system.addForce and pass it your harmonic bond force. And now we have set up all the harmonic bonds in the system. And in practice, of course, you would have lots of other forces, angle terms, torsion terms, non-bonded interactions, etc. You set up all of those in completely analogous ways. The code will look very, very similar. And so I'm just saying here, for all your other terms in the force field, you will do something similar. All right, so we've completely created our system. Now we want to simulate it. So we are going to create an integrator, a Langevin integrator. Now this you've actually seen before, which is, I said that what you were doing before was, working at the level of the higher level application layer. But of course, the application layer is built on top of the public API and still uses lots of classes from the public API. So some classes like Langevin integrators are actually part of the public API, but you use it directly when you're writing Python scripts at the higher level. So, we're going to create our integrator. We are going to create a context, which I told you about, so it combines your system and your integrator. In fact, the class that you saw in your earlier examples, simulation is just a very thin wrapper around a context, really. It just automates some of the handling for you. It manages the reporters and things like that. But mostly it's just a thin wrapper around a context. So we're going to set what we want the initial positions to be, set what we want the initial velocities to be, and then take 500 steps. Yeah?
Langevin is the only integrator that OpenMM uses?
No. We have lots of others. In fact, DeWalker in his talk, he listed off. So we have fixed time step, Verlet, Langevin, and Brownian. We have variable time step, Langevin and Verlet. We've also got a plugin that's a RPMD integrator. It's I don't know if you're familiar with ring polymer molecular dynamics. We've got an integrator that does that. And in fact, in my next talk, I'll be telling you about custom integrator, which is a way you can implement pretty much arbitrary.
So each of them has its parameters, right?
Yeah.
For Langevin, you have temperature, friction,
and time step, right.
And for others, they have their own parameters.
Right. So we've just simulated it for 500 time steps, and now we want to retrieve some state information. So we're going to call getState on our context, and we tell it exactly what information to include. So we're saying get positions equals true, get velocities equals true. So the state that it returns to us will contain positions, and it will contain velocities, and that's it. Like, it won't contain forces because we didn't ask for forces. But we now have the snapshot, and we can do things like just loop over all the positions and print each one out. This is just an example, but that's how you get your information. So any questions on that?
So the context doesn't require topology to create, but the system object does. Is that because the simulation that's because the simulation object contains reporters that need information from the topology?
Right. That is correct. Okay, one other very important class that I didn't really mention, but I should talk about a bit, is called platform. So the thing to understand with this is that the public API is defining an interface. It describes how your code interacts with OpenMM. it does not provide, that does not specify anything about the implementation. The implementation is separate, and it is provided by an object that's called a platform. In particular, OpenMM comes with 3 platforms. The first one is the reference platform. This is really written to be, it's written in C++, it runs on your CPU. It is written to be very simple, easy to understand. Generally, when we're implementing any new feature, we create the reference platform version of it first, and then use that as the starting point for all the others. One important thing to know about it is that it's very, very slow. This is because we make absolutely no attempt to make it fast. In fact, we very specifically do not perform any optimization in it that would make it less simple or less readable, because that's just not what its function is. OpenCL is the one that you should be using most of the time. OpenCL platform is usually going to be the fastest one. It can run on both GPUs and CPUs. It's much more optimized. And so in most cases, you'll want to use the OpenCL platform for all your work. We have one other platform that uses CUDA, which is NVIDIA's proprietary technology. This platform is going to go away in the next major release of OpenMM, and we are going to replace it with a completely new platform that also uses CUDA but shares no code at all with it. In fact, the new CUDA platform will be very, very closely modeled after the OpenCL platform. The reason for this is that the CUDA platform that we have right now was really the very first of all these platforms that was written. In fact, it was created before OpenMM even existed, was created for different purposes, and then we sort of took this existing code and shoehorned it into OpenMM. It's quite old. It's almost impossible to maintain. It's missing a lot of features found in the other platforms. So we are going to get rid of that, and we're going to be replacing it with a completely new CUDA-based platform. The one reason you will sometimes still use CUDA in this version, though, it is the only platform that the only one that currently supports the Amoeba force field. So if you want to use Amoeba, you have to use the CUDA platform. But for pretty much anything else, you'll probably be using OpenCL. Let me describe the API for working with the platform class. So there's just a few things that you'll commonly want to do with them. You may want to specify what platform to use for a simulation. So you would say platform, get platform by name, and give it the name. So we'll say we want the OpenCL platform. And then when we create our context, you pass it as the third argument here. You say use this platform. And when you create a simulation, you can do exactly the same thing. You can pass a platform to use here. If you do not do this, it will just look at what platform's available and pick the one that it thinks will be fastest, which most often is what you want. But there are times when you want to specifically say, no, use this platform. And so this is how you do that. Other times you've created a context and you just want to know what platform it's using. And so you can just, on your context, call context get platform, which will return this platform object, and then get name to get the name of that platform. So this line will just print out, what is the name of the platform that you're using. And one other thing that you might sometimes want to do is just know what platforms are available. And so you could just call platform get num platforms to find out how many platforms there are, and then use that to loop over them and get platform I, get name. And this will just print out a list of all the available platforms. Some of you may have already discovered the API documentation. If you haven't, you should really go and look at it. Wherever you've got OpenMM installed, it will be in the docs directory. So it's this fairly nice HTML documentation. It's actually but we have 2 versions of this, one for Python and one for C++. They're both in there. And this lets you go through, look at any class, get descriptions of what the class does, see all the methods that you can call on objects of the class, etc. And this will really be an invaluable resource for you. Okay, let's talk about the differences between C++ and Python. They are very, very similar. In fact, so we create the C++ API, and then the Python version is just automatically generated from that. But there are a few differences between them that are good to know about, especially if you're going to be looking at API documentation. When you call getState to create a state object, the syntax for them is a little bit different. In C++, you pass in this set of Boolean flags that you OR together to tell it what information you want. For Python, we decided to use a more Pythonic interface for this, and so instead it has this set of arguments that you specify values by keyword to say what information you want. Works the same way. It's just one looks like a C++ interface, the other looks like a Python interface. Along the same lines, Python supports multiple return values. C++ doesn't. The way you get multiple values out of a C++ function is by passing in references and storing things. So you'll find a lot of functions where, in C++, if you've got a harmonic bond force and you want to know, tell me the parameters for the ith bond. Well, in C++, you declare these variables and then pass in references to them to a function, and this function will store those values into the variables. Whereas in Python, you just call get parameters, bond parameters I, and it returns them as a tuple, so as multiple return values. And again, we did this because it would be what feels more like a natural Python interface. One more difference, and this is a very important one, which I'm actually going to talk about a lot. In Python, all your quantities have explicit units, and you actually saw this in the examples where you would do things like specify your temperature as 300 times Kelvin, or your time step as 0.002 times picoseconds. C++ does not have this. C++, we just define a standard set of units, and you have to give all your units and your quantities in those units. But the problem with this is that there's actually a whole lot of different unit systems that are common in MD. Just as examples, some MD programs measure time in picoseconds, others measure it in femtoseconds. You can use either one, but if you think you're specifying a number of femtoseconds and you're actually specifying a number of picoseconds, you're going to get the wrong answer. Distance is commonly measured both in nanometers and in angstroms. Some programs like to measure energy in kilocalories per mole, while others measure it in kilojoules per mole. And I've got some really sad news for you. You will make mistakes about this. I know you think you're a smart person and you can avoid this, but you know what? Humans just are not designed to do this. You will make mistakes about this, and these mistakes will produce bugs in your program. Like it or not, it's going to happen. And so that's why in the Python API, we have tried very, very hard to try to protect you from doing this. Because, let's face it, it's going to happen. And you know what? You're not alone. Lots and lots of smart people make mistakes about this. And probably for you, the consequences are at worst going to be, oh, you publish a paper and then have to retract it because it turned out all your results were wrong. Not like the Mars Climate Orbiter, which back in 1999 crashed into Mars, and that was $125 million down the drain, and it turned out this happened because of a unit conversion problem in the software, such that, like the rocket that was supposed to slow down its descent didn't fire when it was supposed to fire. Another really famous example of this, back in 1983, Canada was just in the middle of switching over to the metric system, and well, for airplanes, they had all these instructions about how to refuel an airplane, and someone who converted some of those instructions from imperial units to metric units made a mistake, and as a result, a plane ran out of fuel in midair. Probably the consequences will not be as severe as this when you make mistakes in unit conversion, but you still really don't want it to happen. So, how do units work in OpenMM? It's really simple. Just multiply each value by its units. 5 times nanometers represents 5 nanometers. Compound units work just fine. 9.8 times meters divided by seconds squared. There you go. Value in meters per second squared. Once you've got this quantity that has units on it, it's really easy to convert it to any other compatible unit. So like if you've got 5 nanometers and now you want that in angstroms, you just say size dot in units of angstroms. And there you go, 50 angstroms. If you want, so this is really what we call a quantity. It's something that has both a value and units. If you want just a pure number, you can also say value in units, angstroms, and then you'll get back just a number, 50. We very much recommend you keep things as quantities, things with units, as long as you can. but there will come times when, like, you've got to pass this value to some other function that just wants a straight number, and so you've got to convert it. But generally wait till the last moment to do that, because that way you have the fewest opportunities to make mistakes. When you do math, the unit conversions will just happen automatically. 5 nanometers plus 25 angstroms, no problem. 7.5 nanometers. This is one of the places it will save you from making mistakes. You don't have to worry about the conversions. It will just do it for you. If you say 5 times nanometers plus 25 times picoseconds, you get an error. Cannot add two quantities with incompatible units, nanometer and picosecond. In other words, you're trying to do something that just makes no sense. If you didn't have these units, no problem. Oh, 5 plus 25, that's 30. But because we've got these units on here, and it knows, like, what are you trying to do? You can't add a distance to a time. It will catch this, and again, this will save you from making mistakes. You can apply units to lists, tuples, arrays, all sorts of sequence quantities, just the way you would normally. So you can, like, take, a tuple here, multiply it by nanometers, and now you've attached units to this whole quantity. You can also convert an entire list at once. So, like, if you want to get the, take a bunch of positions and just convert them all to angstroms, you can just take the list of positions that comes back from state.getPositions and just call in units of on the entire list. Units are optional on all input arguments. So if you are calling an OpenMM function and you pass it a value that has units on it, it will know how to convert that into the units that it wants. It will take care of all the conversions directly. If you give it just an ordinary number, that's okay. It will accept that, but it's up to you to make sure that you gave it a unit or a value in the units it was expecting. And output values that it returns to you will always have units attached to them. OpenMM does have a default system of units when you're working in C++, which does not have explicit units attached to values. It just expects that all values you give it will be in these quantities. So distances are measured in nanometers, times in picoseconds, temperature in Kelvin. Masses should be in atomic mass units or grams per mole. Energy should always be in kilojoules per mole, not kilocalories. And charges are in units of the atomic charge. There's a really important reason we chose this system of units. It's because these form a consistent system. This is not true of many of the common unit systems that people use. For example, any unit system that measures energy in kilocalories per mole is not going to be consistent. For example, F equals ma is not a consistent set of units because force is the gradient of the energy, and ma is mass times acceleration. And if you're measuring your energy in kilocalories per mole, those two sides of the equation will have different units, and so you have to have all these weird conversion factors that appear everywhere. These units form a consistent system, so a force is a force is a force, whether you measure it as the gradient of the energy or as a mass times acceleration. And we certainly recommend using consistent unit systems whenever you can. So which language should you use? Python has a number of advantages. It's much faster to develop things in Python. It really is a lot easier. Python has an interactive mode, so you can just pull up a Python command line and just start typing commands and see what happens, and this is very, very useful to be able to do. And of course, it has the explicit units. So all of these are big advantages of using Python. However, C++ also has certain advantages. It does execute faster. Most cases, this isn't really going to be an issue because all the really computationally expensive things are going to be happening down inside OpenMM. But if you are writing code that actually has to do a lot of computation itself, that will definitely be faster in C++. Of course, it's much easier to call from other languages. Python is, great at calling other languages, but if you've written some Python code and then you want to call your Python code from C++ or Fortran or something, that's a lot harder. It's a lot easier if it's written in C++. And of course, in C++, you can write plugins, and it's the only place that you can write plugins. So that is the end of that talk. Are there any questions on it?